Welcome to an intro to waves. So, light waves, sound waves, radio waves from your phone, or even microwaves that you use to heat up your food are all examples of waves that you might see in your everyday life. But what actually are waves? Well, a wave is a disturbance or oscillation that transfers energy through space or matter. And the matter that waves oscillate through are referred to as media, for example, air and glass. There are two main types of waves, transverse waves and longitudinal waves. But let's start talking about transverse waves first. So transverse waves are waves that oscillate perpendicularly or 90 degrees to their direction of energy transfer. As you can see from this diagram, the wave is oscillating perpendicularly to its direction of energy transfer, where x is the displacement. We're going to talk more about the properties of waves later. So some examples of transverse waves are light and waves in water, like this ripple effect shown, which resembles a transverse wave. Let's now talk about longitudinal waves, which are essentially the opposite of transverse waves. Longitudinal waves are waves that oscillate parallel or in the same direction to the direction of energy transfer. They are made up of compressions and rarefactions, or essentially regions where the wavefronts are very close together and regions where the wavefronts are spread out or far apart. Some examples of longitudinal waves are sound and a slinky. So this diagram here represents a sound wave where the black dots are air particles. As you can see, these regions are the compressions and these regions are rarefactions. Same goes for a slinky here. As you can see here, the individual coils are very close together in a compression, and here they're very far apart in rarefactions. Let's look more at the properties of waves. So this diagram here is a displacement distance diagram. We talked about displacement before, but essentially displacement is how far the wave is oscillating from its equilibrium point, or equilibrium is this axis here. The maximum displacement is known as the amplitude. So these are the displacements of the wave at different points in space. The highest point in a wave is referred to as a crest, and the lowest point a trough. The wavelength is essentially how far the wave travels in one oscillation. And to measure this, we can measure one oscillation from a crest to a crest, or a trough to a trough, or realistically from any point in one oscillation to another, like this. The symbol for a wavelength is lambda. You may also encounter displacement time graphs. And the main difference here is that one oscillation, the distance between one oscillation, is essentially the amount of time it takes for the wave to make one oscillation, or the time period, t. So here, time period is the time taken for one oscillation. And the frequency is the number of oscillations per second, which is measured in hertz, which is essentially per second. The equation to find the frequency is 1 over time period. Let's now look at what might be one of the most important equations in waves, the wave speed equation. V is equals to F lambda, or the wave speed is equals to the frequency times the wavelength. We know that the speed of light is a constant, or 3.0 times 10 to the power 8. So when we look at the visible light spectrum, we can see that as the frequency increases, the wavelength decreases. And vice versa, where red has the largest wavelength, yet the smallest frequency, and violet has the smallest wavelength, but the largest frequency. So we know that frequency and wavelength are inversely proportional. Let's now look at an example question to wrap up what we've learned. So in this question, it says that an oscilloscope can be used to determine the frequency of a sound wave, and the diagram shows an oscilloscope trace of a sound wave. We are asked to calculate the speed of sound, and we are given the wavelength. So let's start off by writing down the formula for calculating the speed of a wave. V is equals to F lambda. Perfect. We are given the wavelength, so lambda is equals to 0.34 meters, which is also equal to 3.4 times 10 to the minus 1 meters in scientific notation. So what we need to find is the frequency. Let's look at the information that we are given. So since we know that this is essentially a displacement time graph, let's try and work out the time period of the wave. So we are told the key that 1 square is equals to 0.5 milliseconds. So let's calculate the amount of squares for the time period. So let's do this from peak to peak. There are 1, 2, 3, 4 squares. So we know that the time period will be 4 squares times 0.25 milliseconds per square. 0.25 milliseconds, which is equals to 1 millisecond. But since we want to use SI units, let's convert that to seconds. So 1 times 10 to the minus 3 seconds. Now we know that frequency is equals to 1 by time period. So frequency is equals to 1 over 1 times 10 to the minus 3 seconds, which is equal to 1 times 10 to the 3, or 10 cubed, per second. But we also know that the unit for frequency is hertz. So now that we know our frequency and wavelength, let's plug it into our original equation. V is equals to F 1 times 10 to the 3 hertz times lambda, which is 3.4 times 10 to the minus 1 meters, which is equals to 3.4 times 10 square meters per second, or 340 meters per second. There. So we calculated the approximate speed of sound. Thank you for watching this video. I hope you found it helpful. In the next video, we're going to cover refraction and reflection.